Hello everyone, welcome to this lecture. So, this will be the part 1 of the analysis of the EIG protocol for perfectly secure Byzantine agreement. So, the lecture outline is as follows. We will focus on the proof of the validity property. The rest of the properties we will discuss in the next lecture. So, just let us quickly go through the EIG protocol. So, we have the EIG data structure T sub NT, which has T plus 1 layers, okay, and each node will have a label associated with it or a tag associated with it. And the idea behind the labeling is that as we go from the root to the leaf node, then the labels that we encounter, it consists of the index of distinct parties. That means it should not happen that the index gets repeated, okay. And each party maintains a local copy of its EIG tree, and in the protocol the parties exchange messages for T plus 1 communication rounds and assign values to their respective copies of the EIG tree, and based on the values which they have assigned, they recompute the values, assign new values, and based on the new values which are computed, the overall decision is taken. Right. So, the initialization is as follows. Each party assigns the bit BI, the input for the Byzantine agreement protocol, to the root, and then for the next T plus 1 rounds, each party PI does the following in round number r. It sends the values of all the nodes in its local copy of the EIG tree at level r minus 1, except for those nodes whose label has the index I somewhere. Okay. So, for instance, during round 1, if we consider party number 1, then it will never send a value which it has assigned to this particular node to anyone, because the label of this node has the index 3 appearing in it. Now, based on the messages which the parties receive during round r, they assign values to the nodes at level r in their respective copies of the EIG tree. This is done as follows. So, if PI has received a message of the form that a node with label I sub 1, I sub 2, I sub r minus 1 has the value v in Pj's local copy of the EIG tree, then what Pi does is that it goes to the child node in its local copy of the EIG tree, which has the label I sub 1, I sub 2, I sub r minus 1 followed by j, and in its local copy of the EIG tree the value v is assigned. However, it could be possible that party Pj is corrupt and it does not send any message, and remember that we do not have separate instructions for messages which do not arrive within a specific round. The nomenclature or the strategy that we follow is that if some expected message does not arrive in a particular round, and substitute it with some default message and proceed. So, if the message comes, fine, well and good. If the message does not come, then the node with this label I sub 1, I sub 2, I sub r minus 1 j in Pi's copy of the local EIG tree is assigned a value v. And once all the nodes in EIG tree have been assigned values, the output is decided based on the values assigned to the respective nodes. Namely, parties now go to their respective copies of the EIG tree and start from the leaf nodes and go in a bottom up fashion. So, they reassign values to the nodes, and a reassignment happens as follows. For the leaf nodes, the reassigned values remains the same as they were earlier. Whatever values the parties have assigned during the T plus 1th round, but as we go up, the new values are computed based on the majority, strict majority of the new values which have been computed for the children nodes, if at all majority exists. Of course, it could be possible that majority does not exist, in which case some default bit v is taken and assigned as the new value. Okay. And once the new value has been assigned to the root node in the respective copies of the EIG tree, the ith party assign the outputs the value which has been assigned as the new value to the root node. That is the decision, that is the output for the Byzantine agreement protocol for the party PI. Okay. And in the last lecture we have also seen a demonstration. So, I hope that the working of the protocol is very much clear. Now, let us prove that this protocol satisfies the liveness requirement and validity requirement. The proof for the consistency we will see in the next lecture. So, the liveness or the termination requirement is that every party should terminate the protocol and should have an output by some specific time. Okay. And that is very trivial to verify, because there are T+1 communication rounds. Okay. And each round will take delta clock cycle, assuming that once a party sends a message in a round, it is received at the end of the delta clock cycles. So, therefore, at the end of time t+1 delta, every party will have the new value ready for the root node, and that is the value which they are going to output. So, termination is trivial to verify. I am not separately going through the proof of the termination property. It will never happen that the parties keep on running the protocol forever, even if the corrupt parties decide not to cooperate, not sending any message and so on. Okay. So, let us go to the validity property, the proof of the validity property. And to recall, the validity property demands that if in the EIG protocol all the honest parties start with the same input, okay, say all the parties start with the input 0, then the output decision of all the honest parties should be 0, and vice versa. If all the honest parties start with the input 1, then all the honest parties should output 1 as the decision at the end of the protocol. Okay. Of course, we do not care anything regarding the output of the corrupt parties, because the corrupt parties can output whatever they feel like. So, to prove the validity property, we will require help of several lemmas. So, let us start with lemma 1, which states the following, that if you have a triplet of parties p I j k and say all of them are honest, then if we take any node whose label is x, and suppose the label x has the last index as k corresponding to party p k, and say p k is honest, then the claim is that the value which is assigned to the node with label x in the ith party's EIG tree and the jth party's EIG tree will be the same. So, it is like saying the following, that you take any node x whose label ends with the identity or the index of an honest party, and there will be a node with this label x in the copy of the EIG tree of all the parties. So, what I am saying is, what this lemma says is that if we take the node with label x across the EIG tree of all the honest parties, then the value which will be assigned by the respective honest parties during the protocol to this node will be the same. It will not be the case that Pi assigns a value say 0 to the node with label x in its local copy of the EIG tree, and Pj assigns the value 1 in its local copy of the EIG tree for the same node. It will never happen, provided we are talking of a node whose label ends with the index of an honest party. and the proof is very trivial. Okay. So, imagine what will be happening in the pk's copy of the EIG tree. So, I am assuming here that x has a label of the form I sub 1, I sub 2, I sub r minus 1 followed by k. Okay. Now, if we consider the pk's copy of the EIG tree during the round number r minus 2, during round r minus 1, sorry, during round r minus 1, pk would have assigned some value say v to the node with this label, right, and during the same round r it would have sent the following message to everyone. It would have informed everyone that the node with the label I sub 1, I sub 2, I sub r minus 1 has the value v in pk's copy of the EIG tree, and it would have sent the same message identically to all the parties, because we are assuming that pk is an honest party. Okay, this lemma is with respect to a label which ends with the index of an honest party. So, pk will not do the following, that to one set of parties it sends v being 0 and to another set of parties it sends v being 1, it will not be the case. Now, consider what happens in pi's copy of the EIG tree and pj's copy of the EIG tree when pi and pj receives this message from pk during round r. They will go to their respective copies of their EIG tree and focus on the node labeled x, and x is I sub 1, I sub 2, I sub r minus 1 followed by k. Now, since pi has received this message from pk, okay, what pi will do? Pi will assign the value v to the node labeled x, and since pj also would have received the same message from pk, it will assign the value v to the node with label x in its copy of the EIG tree, and this holds for other honest parties as well. So, if we take any honest party, right, in their respective copies of the EIG tree, the value v will be assigned to the node whose label ends with the index k, where k is an honest party, right. This lemma does not hold if pk is corrupt. Okay, lemma does not hold if pk is corrupt, because if pk is corrupt, then to pi it might send the value I sub 1, I sub 2, I sub r minus 1 and say 0. That means, it is telling that okay, 0 is the value in my copy of the EIG tree with the label I sub 1, I sub 2, I sub r minus 1, whereas to pj it might send that the node with label I sub 1, I sub 2, I sub r minus 1 has the value 1 if pk is corrupt, due to which pi may end up assigning the value 0 to the node with label x and pj may end up assigning the value to the node with label x. But we are talking about the case when pk is honest. If pk is honest, it will send the same v, due to which this will not happen, right. Now, helping lemma number 2, which is also very straightforward. The lemma states that if I focus on the EIG tree, then at every level r, where r ranges from 0 to t, majority of the child nodes will have a label whose index corresponds to an honest party. Okay. So, again, before going into the proof, you can verify that the lemma is trivially true for this example. So, here n is equal to 4 and t is equal to 1, and assume P3 is corrupt, right. So, if I focus on this node, its children are this node, this node, this node and this node. So, if P3 is corrupt, honest parties are P1, P2 and P4. So, you can see that 3 nodes, namely the node, this node and this node, the circle node at level 1 ends with the index of an honest party, and it is only one node whose label ends with a corrupt party. Similarly, if I go one layer down, right, then among these 3 children of the node with label 1, it is only one node with label ending with the index of a corrupt party, but majority of them are ending with the index of an honest party everywhere, you can see here. So, 1 is honest here, 2 is honest here and 4 is honest. In fact, all the 3 children ends with the index of an honest party. If I focus on these 3 children, then 1 ends with the index of 1 corresponds to the index of an honest party, 4 corresponds to the index of an honest party and only 3 corresponds to the index of an honest corrupt party. So, majority of the children have a label ending with the index of an honest party. So, why this is true? So, in general at any node at level R will have how many children? It will have n minus r children because of the nomenclature, because of the way we have labeled the nodes, assigned the labels to the various nodes. And remember, the EIG protocol assumes that n greater than 3t holds. So, if n greater than 3t holds, then for every r in the range 0 to t, the condition n minus r greater than equal to 2t plus 1 holds. That means, out among the n minus r children, at most t can be corrupt, at most not at most t children could be corrupt, at most t nodes end with an index of a corrupt party, and at least t plus 1 nodes have this property, that at least t plus 1 nodes have label ending with an honest party. Okay. And remember that each child node has a label ending with the index of a distinct party. So, among these n minus r children, it will not be the case that if we focus on the last index, repetition occurs, no. So, that is why this lemma is trivially true. If I go one layer further down, that means, if I make r equal to t plus 1, then this lemma need not hold, because then there will be only 2t children, and among those 2t children there might be t children whose label ends with the index of a corrupt party and t children whose labels end with the index of an honest party. In that case, strict majority may not be there, but in the protocol we do not go beyond level or beyond the level t, okay. Because during the t plus 1th round, only the values of the nodes at level t are communicated. Okay. Now comes the very crucial lemma, which states the following, that if I focus on any node with label x and it ends with the index of an honest party, then in every local copy of the EIG tree, okay, corresponding to the honest parties, that means, if I consider the party pi and if party pi is honest, then the old value of the node with label x will be the same as the new value for the same node. It won't be the case that the old value was different and the new value which is computed based on the majority rule is different, and this holds with respect to every honest party's local copy of the EIG tree, provided the node x ends with the index of an honest party. Okay. Now, this proof will be done through a backward induction on the size of x. Why size of x? Because this lemma is for any x. So, x could be of size 1, that means it could be as simple as that x occurs as x is the label of a layer 1 node, or x could be a string of size 2, that means x, the lemma even holds for the nodes x which are occurring at layer number 2, or x could be a string of size t plus 1, that means lemma even holds for a node x occurring at layer number t plus 1. So, we have to prove that this lemma holds irrespective of the position or the layer number of x. So, that is why to prove it for any x whose label ends with the index of a corrupt party, we are going to use a proof by induction, and the induction will be a backward induction. That means, we will first start with the leaf nodes and we will keep on going from leaf to root and prove it is true for all the layers. Okay. So, our base case will be when x is the label of a leaf node. So, assume that x is a leaf node and it ends with the index of an honest party. So, we want to prove that across all the copies of EIG trees corresponding to the honest parties, the new value which is assigned to x will be the same as the old value. So, for that we will trigger the lemma number 1 first, and lemma number 1 states that the old value which is assigned to the node x across all the copies of the EIG tree by the respective honest parties is same. Say a value v is the old value which is assigned to all the in all the EIG trees. Now, recall that the way new values are computed for the leaf nodes, the leaf value of x, for the leaf nodes x, the new value is same as the old value. Okay, that is the way new values are computed. We do not apply the majority rule for the nodes labeled x, where x corresponds to a leaf node, because since it is a leaf node it does not have any children. So, how can we apply the majority rule? So, the new value for x will remain the same as the old value of x if x corresponds to a leaf node, and from lemma 1 the value which is assigned, or the old value of the node labeled x is same across all the EIG trees. That also implies that the new value for the x also remains the same across all the copies of the EIG tree. So, the base case is done. Now, assume the inductive hypothesis, assume that a statement is true, that means the lemma is true for a node, any node x occurring at layer k plus 1, and now we go one layer further up. That means, now we are taking the case when x is of the label of x is a string of size k, that means x is occurring at layer k, and say the label of x is I sub 1, I sub 2, I sub k, which are all distinct, and p k is an honest party. That means, the index k corresponds to the party p k and p k is honest. Why honest? Because we want to prove the lemma for all the x whose label ends with the index of an honest party, not corrupt party. Okay. So, what we know, what is going to happen in the protocol, and what exactly are the things which we already know. So, again let me trigger lemma number 1 for this node x occurring at layer k, and what we know is that across all the EIG trees corresponding to the honest parties, the old value which is assigned to x is a common value. Okay. That means, in Pi's copy of the EIG tree the old value of x will be v, and in Pj's copy of the EIG tree the old value of x also will be v, and if there are other honest parties in their respective copies of the EIG tree, the old value of x will be v. That comes from lemma number 1. Now, we want to prove what is our goal? Our goal is to prove that even the new value which is computed for the node labeled x across all the honest parties EIG tree based on the majority rule also remains the same, namely v. So, for that the first thing to observe is that during round k, what every honest PJ would have done? Every honest PJ would have communicated the message that, hey, in my copy of the EIG tree, the value of the node labeled x is v, and it would have sent this message identically to everyone. Sorry, it would have happened during round k plus 1. Sorry, it should have happened at round k only, because we are considering the case when x is a node at layer k. Okay. So, PJ would have sent a message x v to everyone, Pi would have sent a message x v to everyone, and so on, and all other honest parties would have sent a message x v to everyone. Of course, the corrupt parties might send that, okay, in their respective copies of the EIG tree, x has the value v prime, where v prime is the complement of v. Okay. Corrupt parties can behave arbitrarily, but okay. So, before going into that, before proceeding further, what we are going to see here is that because every honest party PJ sends this message x v identically to everyone, what is going to happen is that if we focus on the children of the node labeled x, there will be children which will have labels of the form x followed by the index of an honest party. Those indexes could be j, I and other honest parties. The old value which will be assigned to the nodes with, or to the childrens with label xj, xi and x followed by the index of an honest party will be v, because as I said, all honest parties will be sending the message x followed by v to everyone. And now let us, and let us now apply the inductive hypothesis. Let us now apply the inductive hypothesis, and as per the inductive hypothesis, since the children are now appearing at layer k plus 1, level k plus 1, and we have assumed that the statement is true, the lemma statement is true even for nodes which have labels of size k plus 1. So, if we focus on all the childrens of x whose label ends with the index of an honest party, the new value and the old value for such nodes will be v only. That comes from the inductive hypothesis, and now we can apply, we can trigger the lemma 2, which states that if we focus on the node x, okay, label with the, if we focus on the node with label x, majority of its children will have the last index corresponding to an honest party. Okay. And such nodes whose last index corresponds to an honest party, their new values will be the common v, that comes from the inductive hypothesis. Due to this, when we apply the majority rule, v means when the parties respectively apply the majority rule in their respective copies of the EIG tree to compute the new value for the node x, it will turn out to be value v only. So, the old value also remains the v and the new value also remains the v, it will not change for all the nodes x irrespective of at which layer they occur, provided x ends with the index of an honest party. Okay. So, now we will use the lemma number 2 and lemma number 3 which we have proved to conclude our validity proof. So, the theorem statement is, the validity statement is that in the EIG protocol, if all the honest parties start the protocol with the same input bit, say v, where v could be either 0 or it could be 1, Then after exchanging messages, assigning old values, computing new values, each party will have the decision output V only. That means the old state V remains the same, it does not get changed. So, how do we prove this? So, without loss of generality, assume that the parties P sub 1, P sub 2, P sub n minus t are the honest parties. Remember, there are at least n minus t honest parties and at most t corrupt parties, and their exact identities will not be known. Okay. But what we will know is that there are at least n minus t honest parties. To do the analysis of the validity statement, I am making a simplified assumption that okay, imagine that the first n minus t parties are the honest parties, but this is without loss of generality, because whatever we are stating here as the proof carries over for the general case where the n minus t parties are scattered, means their indices need not be consecutive. Okay. Also, note that n minus t is strictly greater than 2t because n is greater than 3t. So, during round 1 what would have happened in the EIG protocol? During round 1 P1 would have reported to everyone that its input is V, P2 would have sent, so P1 would have sent a message delta V to everyone, P2 would have sent a message delta V to everyone, because we are assuming that the inputs of all the honest parties are same, and P of n minus t, P sub n minus t would have sent a message delta V to everyone else. Of course, corrupt parties can send different versions of their input to the respective parties. Now, due to this, at the end of the round 1 what would have happened? Every honest party Pi, it would have assigned the value V to the nodes with label 1, 2 n minus t. I do not care what values it assigned to the nodes whose label ends with the corrupt party. Okay, I do not care. Now, what does lemma 3 states? Lemma 3 states that the old value which has been assigned to the nodes with label 1, 2 up to n minus t will be same as the new value. Okay, that means the recomputed values will also remain the same, namely V. And from lemma 2, majority of the child nodes of this root of the EIG tree will end with the index of an honest party, namely there are n minus t children whose label ends with the index of an honest party, and n minus t is more than 2t, that means at least 2t plus 1, that means the majority of them are ending with the index of an honest party. So, by the majority rule, every honest party will assign new value as V to their respective root nodes, and that will be the overall output of the EIG protocol. So, that completes the validity proof, and that also concludes today's lecture. So, these are the references which have been used. So, I have used heavily the material from MIT's distributed algorithm course, and of course, the full details of the EIG protocol and proof you can find from any of these 2 textbooks. Thank you.